Hey Team Electronics and Coding, welcome to your first screencast. So screencast is a little video lecture where I give you a lecture outside of class. I'm gonna write, I'm gonna highlight, I'm gonna use a laser, and you're gonna listen and take notes. Now, the reason for doing these screencasts is I want to, as much as possible, avoid lecturing you in class so we can reserve class time for tinkering and building. However, there is some information that you need in order to understand what's going on in this class. Hence the screencast. Easy way for me to deliver you information. You should watch and take notes just like you would in class. Write down questions that you have on the side because there'll always be time in class to answer those questions. And yeah, okay, here we go. First one. So here's a copy of the circuit that you set up in class, I don't know, depending on when you're watching this screencast today or yesterday or a few days ago. And yeah, it looks just like this. Now, we could, this is what we had in class, and this circuit diagram is actually showing us this exact same representation here. So this diagram is the simplified equivalent of this system right here. Okay, so how do you read a circuit diagram? Well, the easiest thing to read are the wires. So any little straight line is going to indicate a wire, or maybe I should just even more simply say it's an electrical connection. Now, you probably noticed when you were playing around with the circuit that if you disconnected any part of the circuit, the light went out. And this is because you created an incomplete circuit. You disconnected part of the circuit and you prevented electrons from moving in a full loop, and then the light went out. Okay, so a complete circuit has a battery, or I guess maybe power source more generally, that is indicated by these two horizontal lines. Now, the longer line represents the 5-volt side of the system, or also called the power side or the positive side. And the shorter hash mark represents the ground, or the negative side of the system. It also 0 volts. So in order for a light to turn on, we need to have a connection between the power side of the system and the ground side of the system so electrons can flow all the way from one end to the other. Okay, what else is in our circuit? Well, this little arrow with a line going through it represents our LED. And this little squiggly line down here represents a resistor. So these are all the components in our circuit. A battery or a power source right here, our Arduino, the LED right here, all the electrical connections between, and the resistor right here. Okay, so we're going to practice representing circuits in this kind of layout like we would see with our kit, as well as circuit diagrams like you see below. Okay, you probably noticed when you played, or I guess I should say, this circuit diagram is showing us a direct connection, and it's really easy to see how electrons flow from one side of the battery through the circuit back to the battery again. Here, it's a little bit harder to see how these connections move because we've got this weird thing right here called a breadboard. This is a breadboard. I actually don't know why it's called a breadboard. I should look that up. If you take the breadboard, flip it over, and peel off the sticky foamy backside, which I don't recommend doing because it can be hard to put it back on, but maybe just peek a little bit, you'll notice that you can see these metal bars underneath the breadboard. And this shows you how all of these little wells of the breadboard are electrically connected to one another. So for example, in the orientation of the breadboard I have now, this is a column. Column 30, these little wells are all electrically connected to one another. Column 29 is the same. Column 28 is the same. F through J are electrically connected, but column 30 on the other side, A through E, these are not electrically connected between them here. So in order to get an electrical connection from A to F, for example, you'd have to string something conductive between any one of these wells to any one of these wells. Okay, so the entire middle portion of the breadboard, all these connections are running vertically. The outsides of the breadboard, these connections are called, this is called our ground bus, and this one is called the power bus. These electrical connections are running horizontally, like so. So the same would be true down here. Now, the breadboard is a rapid prototyping board, but there's nothing about it that says that this ground bus actually has to be ground. What determines that it is ground is that you plug it into a ground on a battery, and the power, the only thing that turns this into a 5-volt power bus is connecting it to a 5-volt power source. If you flip-flop these wires, you will turn this into power and this into ground. I do not recommend doing that. It's really helpful to always plug power into power and ground into ground. Troubleshooting will be much easier if you follow this convention. It's also pretty helpful, as you learned in the activity today, the color of the wire doesn't matter in terms of conducting electricity. A wire is a wire is a wire, but we always have red indicate power and black indicate ground. Just keeping ourselves organized and knowing what's what. I really highly recommend that you stick to these conventions, because when you invariably have a bug or a problem in your circuit design, if you know that your black is ground and your red is power, you're going to be much closer to identifying the issue than if you just are using any color willy-nilly in your design. Okay, so if we trace the path of our complete circuit with our LED system here, we'll go from the 5-volt side of our power, and you know that these are all electrically connected, so we pass through here, through this wire, which is electrically connected here to the LED, so we go through our LED, and then the LED is connected to the resistor on this side, and then these are connected to this ground wire, and then back to ground here. So we have a complete circuit. If we break any of these connections, the LED turns off because we no longer have a complete circuit. Okay, an LED. This stands for light emitting diode. Okay, the light emitting part, pretty self-explanatory. When you plug it in, it shines out light. The diode part is maybe a little bit more confusing. You might have noticed that the LED had a directionality to it. So one leg of the LED is a little bit longer than the other leg. Usually we bend the long leg, so when it's inside the breadboard, you can see which leg is which. So one leg of the LED is called the anode. And the anode, we always plug in to the positive side, or power, or 5 volts. And the short leg is called the cathode. And the cathode always plugs into the ground side, the negative side, or the 0 volt side of the system. If you reverse the direction, if you attach the anode to the ground and the cathode to the power, the LED won't light up. So that's the diode portion of this. A diode only allows electrons to flow in one direction. As a result, an LED is what we call a polarized component. You have to plug it in a certain way in order for it to work. Okay, so that was the LED. Second up, we have the resistor. Resistors come in a variety of values. The value that the resistor is actually indicated by the banding pattern on the resistor. We can learn the bands, but resistors are also very inexpensive, so we might sometimes be a little bit wasteful, and if you have a resistor and you don't know its value, you might just want to get rid of it and grab one from your pack that you do know the value of. But if you're interested, I can teach you how to learn these values. A resistor can have a variety of different values. I believe that we were probably, I don't remember exactly, but we probably started out with 220 ohm resistors, or maybe 330 ohm resistors in the original circuit design. And then you manipulated the value of the resistor. You turned it up, you made it much bigger, or you made it much smaller, and you saw what happened to your circuit. Okay, you probably noticed that when the value of the resistor got really big, the light got really dim. And when the value of the resistor got really small, the light got brighter and brighter and brighter and brighter and brighter until it virtually caught on fire. So there's a reason for that. It's called Ohm's law. Ohm's law tells us the relationship between 3 different variables in our circuit: voltage, current, and resistance, VIR. Ohm's law states that voltage is equal to the current times the resistance. So let's write this out. The V is equal to the voltage. I is equal to the current. And R is equal to the resistance. Okay, let's start with V, the voltage. The voltage is the electrical push of the system. For us, it's going to be determined by our Arduinos, or potentially the size of the batteries that we use. So when we hook a battery up to our Arduino, most of the pins on the Arduino are 5 volts. So the voltage that we're mostly going to be working with is 5 volts. The current is the speed that the electrons are moving through the system, or I guess I could say like the number of electrons that pass by a certain point in the system at one time. So just like a current of a river, more current means more water flowing down a river. More current in an electrical system means more electrons flowing through the circuit. Okay, and then last up is the resistance. This is the difficulty of electrons moving through the circuit. Whoops. So, all electrical components have resistance. Even wires, for example, have a very small amount of resistance. But resistors have a kind of determined resistance, and we can use them to control the speed of electrons through our circuit design. So, for example, if we started out with a 5-volt system and a 220 ohm resistor. Now, when we did that, the light lit up. If you swapped out that 220 ohm resistor for a larger resistor, this R value increased, it went up, but the voltage stayed constant. So as the resistance got bigger and bigger and bigger, the current got smaller and smaller and smaller and smaller, and the light became more and more dim. Now, if you took this resistor and you made it smaller, now the current through the light increased and the light got brighter and brighter and brighter up to a point at which it exploded. So, that being said, for a 5-volt system, a 220 or 330 ohm resistor is a good size for an LED. It will light up the light, but it won't let it burn out. If you burn out an LED, not a big deal. Throw it away, move on. Okay, the resistors, unlike the LEDs, are not polarized. It doesn't matter which way you add them into your circuit. You could put it in this way, or you could rotate it 180 degrees and put it in, and it would work the same way. So an LED is a polarized component. A resistor is not polarized. Okay, I think that's it. Thanks for watching. See you in class.